With me is Marco Souza from Locus.
Hello there, everyone.
And we're presenting tonight how you can build an app using Python and Cartesi. So the first thing here is the agenda. We'll get a quick overview of how Cartesi works, the development overview of regular Web 2 applications, then Web 3 using Ethereum, and finally an overview of how it looks like with Cartesi. And then we'll go a bit deeper. So we'll introduce our Cartesi rollup solution. Later, we'll drill down on the external interfaces you will face as a developer. And finally, we'll go to a Python example, a really simple one, on how you can use that to make a minimalistic DApp using our tech. And on the second part, Marcus here will show a much more complex DApp he's built, which is a KNN iris classification flower. Okay, so beginning with the overview, not going to take a lot of time in there, I promise. So the first thing here is that we are doing something really groundbreaking. We're putting an OS, a complete Linux solution inside blockchain. So just for the developers eager to know what it looks like when you're developing with us, it's not hard. It's not like Solidity all over the place. It's not some strange code or some fake Python. So this is actually the backend you're going to see when you're developing with Cartesi. You import real libraries, and it's basically Web 2 development, right? So you're handling things, interacting with traditional HTTP interface. So what's the main idea behind Cartesi? So everybody's used to Web 2, right? We have the servers, everything is centralized, you interact with them, they decide what's the truth, they decide whether you can interact with your application or not. Now, a while ago, we had Ethereum, and Ethereum is awesome. Why? Because in Ethereum, there's no singular party telling you what can be done or what cannot be done. Ethereum is secure, it's censorship resistant, and it's decentralized. But all these great things, they come with a cost, right? So basically, when you're dealing with Ethereum applications, everyone, all these thousands of nodes, they're doing every single thing that's happening in the network. And why is that? Because that way, you cannot tamper with what's happening. If you want to lie about something, well, you're not going to make it. Because to do that, you have to convince thousands of nodes. And well, that's good, but that comes at a cost, right? So just like when you go to a restaurant and you try to decide with like a large group of people, and that takes time, that's the stuff that happens in Ethereum, you know? So basically, all the nodes, they need to communicate one to another, broadcast whatever they think the truth is, and reach a consensus. And because of that, all the transactions, they must be tiny. Because otherwise, everyone is doing all the stuff all the time. If you have really large tasks, then you're just going to break the network. It's going to get clogged. But our idea is, OK, so can we have all this greatness of Ethereum, but enabling really large and complex computations, the ones that enable us to do really interesting stuff like we do on Web 2? And that's the idea behind Cartesi. So how do we achieve that? Well, an overview is here. So in order to do that, we've developed a really cool machine. We call it the Cartesi machine. And this Cartesi machine has a couple of interesting properties, right? So the first thing is that it's not based on the EVM like other solutions that try to scale Ethereum. It's actually based on a real-world processor called Risc-V, which for the ones that don't know, Risc-V is an open platform that was developed by the guys from Berkeley. And the cool thing about it is that being a regular processor, like the ones we have on our phones and our computers, we can actually put an operating system on top of it. And that's what we did. We put Linux on top of it. And then, as a developer, you must know that this is huge, right? Because you don't have to do everything from scratch. There are thousands of brilliant minds that have built all these libraries, all these systems on top of Linux. And well, we're enabling that for you when you're developing your Web3 application. So talking about the Cartesi machine a little bit, the Cartesi machine is deterministic, and we need it to be that way because otherwise we cannot use the same guarantees that Ethereum provides us. Our dispute protocol, which enables us to have these wonderful computations outside, and guarantee the security, it needs the Cartesi machine to be deterministic. As I mentioned, Risc-V is an open hardware, so it's auditable. There are thousands of researchers around the world looking at it, making it better. It's a platform processor, as I said, so the same thing that you're used to having on your computer. And the determinism of the machine just means that whatever you throw at the Cartesi machine, if someone else throws the same stuff, it's going to achieve the exact same result, right? And well, that's pretty cool because now you have a decentralized application that's not simple. You can do really amazing stuff inside of it. So much more processing than you're used to. And well, using every library and language you're used to. It's not a very low-level language like Solidity. Then another major difference of us is that, as I said, Ethereum, everyone is processing everything. Now with Cartesi, it's different. So imagine you're at work and you have to do every single thing that everyone in the company is going to do. You're going to get tired and you're not going to make it, right? So that's what happens when Ethereum gets clogged. It's just that all the nodes, they have too much demand and everybody has to do everything. So with Cartesi, we have a different tactic, which is, okay, so not everyone is going to do everything. We have a couple of nodes doing particular stuff in which they're interested at. That means that when you have a DApp on Cartesi, you have a couple of nodes that are interested in it, and they're going to check if that's correct or not, right? We call that local consensus, and we have a roll-up solution based on that. The third part of this, which is really interesting in our solution, is we have this verification game protocol we use, which ensures the security. So if you guys remember, I just said that when you have Ethereum, it's so safe because in order to control the majority, you have to tamper with thousands of nodes. And as you know, if you have a computation that you don't have thousands of nodes handling, let's say 3 or 4 people, it's really easy for you to convince like 1 or 2 guys to lie and tamper with the computation, which is why our protocol doesn't rely on this local consensus of the few people that are interested in the computation. It actually runs on top of the consensus of the underlying blockchain. So if you have an Ethereum backing Cartesi, for instance, that means that when you're in dispute, you don't have to tamper with the 3 or 4 people that are handling the same DApp as you are. You actually have to tamper with the entire network of Ethereum. And that's really hard to do. Let's just exemplify here a bit what I said. So this is what happens when you're on Ethereum. Basically, all the nodes in all the network are doing everything. And they really get clogged easily because, well, it's a lot of computation that must be replicated by everyone. And in Cartesi, this local consensus that I mentioned works like this. So you have different applications, and not all the computers are running them. Just the interested parties. So for instance, in this DApp, we have like 2 parties, in the other 3, and in that B here, exemplified, we've got plenty more. But the beautiful thing is that every node can choose what DApp they're interested in, and then can validate it. Now, I'm going to talk a bit more about this verification game protocol I said. So the point is that whenever you have a dispute, if someone feels the result is incorrect, what they can do is they can just go to the underlying blockchain, which can be Ethereum or any other one, and they can raise the dispute. What happens is that, given that the Cartesi machine is deterministic, we have this protocol called verification game, in which the first part, we just say, okay, so if I do this and you do this in the Cartesi machine, we must reach the same result. If that didn't happen, what means is that at least in a certain point, we had exactly the same Cartesi machine, and then we did something different. And the protocol tries to identify this point in its first part. Then, once this point is identified, well, how do you settle who's correct? And that's the beauty of it. So we had the Cartesi machine implemented on top of the blockchain as well. That way, we can pick this instruction in which we don't agree, and we just tell Ethereum who's done it right by executing this instruction on this Cartesi machine equivalent implementation on top of the blockchain. And once the blockchain executes this instruction, you can have the assurance that it's going to say, hey, you did the right thing, you're fine, or no, you didn't, you tamper with the computations, you did something that you shouldn't, and then you can be defeated by it, right? Yeah, that's a really strong guarantee. So
Yeah.
just a single party can just enforce the correct result. Now, why is this so good, and why do we do all these computations without clogging the underlying blockchain? So what happens is this. Here you have Ethereum, and all the blocks are being generated like they usually are. So you have data, you have transactions in here, and transactions, for the people that don't know, is the technical term for computations that happen inside the blockchain. Now, when you have a Cartesi computation happening, what goes on is that you go into the blockchain and you just submit a signature of the state of your Cartesi machine when you start this computation. And then you do the whole computation inside your Cartesi machine, and the Ethereum doesn't really have to care about it. And once you reach the end, you just go there to the blockchain and you put a signature of the final Cartesi machine state. And once you do that, all the interested parties, they just observe these transactions, and they fire up their own Cartesi machine. They do exactly the same computation, and when they reach the end, they go and they check the signature of the Cartesi machine. Does it match the one that's on the blockchain? Yeah, we're fine, don't have to do anything. No, then we engage on the verification game. Now let's do a quick check on how development looks like both on Web3 and Web2, and then finally how we do it on Cartesi. So developers that are used to Web2 will find this figure really familiar. So basically what you have on Web2 is you have the clients, which generally run on a browser, and then you have your backend that runs on a server. So the browser is generally your front end, and what you do is you develop an application using one of the famous frameworks, like Vue, React, Angular, and the technologies that are involved are HTML, CSS, and JavaScript. And once you develop your application, it communicates to the server using HTTP or an HTTPS connection. On the server side, on the other hand, you have a web service or something similar that is talking to your front end and can use many services. So you can use databases, you can use NoSQL solutions, you can use whatever you like, right? And that's the traditional model in which we develop. Now, for people that are used to Web3, this picture is going to look familiar. So what happens in Web3 is that you still have the browser, you still have the front end using Angular, React, Vue, or whatever framework of your choice, still using HTML, CSS, and JavaScript. But now you have a new element. And this new element is a library, which is used to connect to the blockchain. And this library is usually called a Web3 client, and it communicates to the blockchain using a protocol called JSON RPC. Once you have this communication, what happens is that you talk to one of these decentralized nodes that are part of the blockchain. And you interact with them, both reading stuff from the blockchain or also writing stuff on the what's called the smart contract, which is the software that runs on the blockchain. Now, how does a Cartesi application look like? Well, it's a bit different. So what you're having here is you have your traditional front end using Angular, React, Vue, or whatever you're used to that still makes usage of HTML, CSS, and JavaScript. But then you also have a couple libraries to interact with the Cartesi rollups framework. And inside the Cartesi framework, you have a connection to the Cartesi machine. And for the convenience of the developer, we have a service that translates the entire iteration with the framework into an HTTP interface. Why? Because, well, most of the developers are web developers, and they're used to interacting with this kind of interface. And the part that you actually have to worry about is this backend here, which talks using HTTP. Now, let's go through a quick introduction on how the Cartesi rollups actually work. So the previous figure, it just stated libs, and now we're going to break down on exactly how it works. So basically, your front end will interface with the Cartesi rollups using 3 different interfaces. So the first one is a JSON RPC interface. And that's just the same interface you use when you're developing with Web3. Why do we use it? Well, when we have our computations on the Cartesi rollups and we want to verify them, well, you have to re-execute them. How do you do that if you don't have the data? And that's why we use the blockchain for it. Whenever you have new data to be provided to a Cartesi machine, it's inserted in the blockchain. That way, no one can claim that it wasn't available, no one can censor you, and you can always validate your computation because you always had the parameters you need. Now, generally, we use a secure blockchain like Ethereum under Node. And as it is Ethereum, well, it's a JSON RPC interface, just like on a Web3 regular application. But as I just mentioned, we just use it for putting inputs on the rollups, nothing else. Now, the second interface we have is a HTTP REST interface. And this interface is used for something really important, which are inspects. Inspects are a way that you have as a developer to communicate with the Cartesi machine and do something without any cost. So it's not a transaction, you're not going to spend gas or any other token. It's just a direct connection. You go to the Cartesi machine and you ask for something that's relevant for your front end. So let's say you're playing a chess match, for instance. One way for you to open your app on your mobile and continue that match is going through all the inputs on the blockchain, check that you have an open match, reproduce all the steps, all the moves by all the players until you reach the current configuration of the board. But that's not really easy, right? Because, well, it's a lot of trouble to get all this information on the blockchain, and then you have to reprocess all the match up to the point it is. So that's where inspect comes in. Inspect is a way for you to just go direct to the Cartesi machine, say, hey, this is my ID. Do I have an open match? Yeah. Okay, what's the board configuration? Here it is, and it's white player's turn. So instead of just redoing the whole computation, you just have the entire current state there for you. It's really useful for user interfaces, as I mentioned, and it's also really useful as a debugging tool because you're not constrained to what the blockchain offers, and you have just complete liberty to ask your Cartesi machine the information you need. Now let's go to the third and final API you use when you're on the front end. It's a GraphQL API. So this GraphQL is a really interesting interface. It was developed by Facebook, if I'm not mistaken. And it's just a way for you to ask a couple of things to the Cartesi machine. So inside the Cartesi machine, we have some ways to output data, right? And there are three kinds. There are reports. Reports are ephemeral stuff, and they're equivalent to Ethereum calls. So basically, you can query something that's relevant for you at that moment, and then you throw it away because it's not really relevant forever. We have a second kind of output, which are called notices. And these notices are equivalent to Ethereum events. So they're generally something that you want to state for the future, and anyone can just query them and just use it. So for instance, given the chess example, if I win a match, I'm going to use a notice because later on someone can use that on a betting DApp or something else. It's just a relevant fact that can boost my score rating or anything like that. And the third interface we have are vouchers. And vouchers are really interesting. So the Cartesi machine, in order to be deterministic, it needs to be isolated from the world. So it doesn't have internet or network access. But it's really useful for a DApp to just issue a transaction, either to another smart contract or to itself. And then that's the way you do it. It's a voucher. A voucher is an interface we have for the Cartesi machine to issue a transaction. And then on the outside, you can query using this GraphQL interface and enforce it. Okay, but given all these interfaces, what does developing on the Cartesi machine looks like? And then we're going to get back to that simple example I just showed on the start. So on this left side, we have the interaction of the front end. So if you check this repo here on GitHub, you can have the code of the program that's being used in here. It's just a command line interface front end that we have. It's done in TypeScript. It's really useful, especially for development. And here on the right side, what I have is a minimalistic version of the echo example we have here on this GitHub repo. So what does this echo application do? It's really simple. So pretty much everything you throw at it, it just throws it back to you, okay? It's just a simple example for people to really understand how easy it is to use our API. So if you take a look in here, it's just regular Python code. Just as I said in the beginning, you import real libraries. After all, you're in Linux, right? And you interact with our framework just like you would interact with a web API. So the first thing here that we have is interacting with an interface. You just generate an input for it. So if you go on your terminal using this front-end CLI, and you do this command yarn start input send with the parameter payload, and you put here hello there, for instance, what's going to happen is that this front-end will generate a transaction on the blockchain, sending this data. Our framework is going to process, and later on, you're going to receive inside the Cartesi machine. Now let's take a look at the code. So the first part here that you can check is that you're importing real libraries that you're used to on Linux. So OS is basically a Python module that allows you to handle some things that you can interact with the operating system. The reason we're importing this is because we want to read an environment variable. So it's going to be useful later on. Now here we're importing requests. For Python developers, request is a very well-known HTTP client. In this line here, we're just making use of this OS module that we just imported because we want to retrieve the value of an environment variable. In this case, it's the variable that's going to tell us where should we communicate with that server that I showed a few slides before that presents the HTTP interface from our framework. Then here we're just defining a simple dictionary, and in this dictionary we're mapping two keys to two methods we're defining here. And this is the main part of the program. So in here we just have the interface for the main interface of the Cartesi framework. So most programmers are familiar with iterators, and the basic structure of your DApp is just an iterator. So whenever you receive an input, you process it, and you call this method here. And once you call it, you do two things. The first thing is you tell the framework if the last thing you processed was correct and you accept it, or if you reject it. And later on, when this guy returns, it provides a response with the next stuff you should process. Here, we're just getting this response, and again, it's just a regular HTTP response you're used to when you're dealing with web development. And you have a very important metadata on this response, which is the request type. Why do we need this request type? Because if you remind, you will have two kinds of interactions when you're handling with the Cartesi machine. So the first one is actually an interaction that advances your application state, which is the one that comes from the blockchain. And this metadata here will have this advanced state value when it's the case. The second kind of input you might receive is that interaction that I explained with the chess DApp. So like you open your mobile and you want to know how the game is going, and you just want to retrieve one time the current state of the application. That's the inspect API. And if it's that kind of input, you'll be having this metadata with the inspect state value. Once you define which kind of input you're dealing with, it's time to process it, right? So that's the next line we have here, which is the handler, considering request type. So let's say it's advanced state. So it's a real input that's going to advance your application state and that you should process. So here we have a definition of a method that's going to handle it, and it receives the payload from that request as a parameter. So the first thing we're doing here, since it's an echo application, like I said, and we're just throwing back stuff that we receive, is we're going to create a very simple dictionary with a payload entry, and the value of it is just going to be the data that we're receiving. Once we have that, we interact with that endpoint I mentioned earlier, the notice one. And when we do a post on this notice endpoint using this payload, we just have on the outside of the Cartesi machine the GraphQL interface exposing a notice with the content we provided, in which, in this echo example, is exactly what we received, right? On the other hand, if it's not an advanced state, if it's an inspect state, in this simple code, what we're doing is calling this handle inspect method. And this handle inspect method, as an echo application, is doing just the same stuff we did with advanced state. So it's just creating a very simple dictionary, which has a payload entry with the content that was just received on the input. Now what we do is we stress a second interface we have. So first we use the notice, which is the one that doesn't go away, right? It's permanent, it stays in there for you. We're using the report one. The report one is also an interface that accepts whatever payload it's useful for you, but it's generally used for ephemeral stuff. So it's that instant board configuration I was talking about before. And the last final thing that's really important, it's returning if you accepted or rejected the input. So in this very simple example, we're never rejecting, but on a real application, when it doesn't make sense, you should reject the input you received. And the final thing that happens is once you return from this handler, you're going to pick up this accept, and you're going to put on a status, so that the next time you call this finish endpoint, iterating to the next step, you just say, hey, I accepted this input, or no, I rejected it. Now, once your software has processed whatever input you throw at it, and in this case, we just generated an advanced state one because we're going through the blockchain, we just want to check this notice here, right? So how do you do it in an easy way? So again, on this front-end CLI interface that we built, we have this notice list command. And what it does, it connects to the Cartesi node, goes into the GraphQL interface, and queries the notices. And if you do this, you get something similar to this. So the payload here is hello there, which is exactly what we had in the input. Because on this very simple DApp, as I explained before, we're just returning whatever we received. And that's what you should see. Okay, so this is just the basic DApp you can have using Python. And let's go for something more fun. So if you want to make your own DApp, we really have a very nice way for you to get started. So if you check out this repo of ours, which is the rollup example, there are tons of examples, not only in Python, but also in other languages. And in there, we have something really nice, which is a way for you to generate your boilerplate code for a Python application. And if you check these custom dApps, there's a README in there. And if you follow the instructions, you'll be able to bootstrap your own Python application. Now I'm going to hand over here to my colleague, Marcus, to explain a more powerful application he developed using Cartesi rollups and Python.
Thank you, Carlo, for all the explanation behind the KNN DApp, and it gives me floor for explaining what I've done with this DApp. And okay, let's get started. This KNN DApp is like a dataset for a common dataset when we're learning about machine learning. So it premises like predicting flowers species given by measurements of these iris flowers. It's like a mood class classification problem. When we are learning concepts about machine learning and all the things related to machine learning, mood class classification will happen a lot, and there is a lot of problems in this area at all. But for this one in specific, we can solve it like using these techniques, machine learning techniques, to create a model and we can use this model to predict the species, in this case, of course, using those inputs. So why I'm using KNN for this example? Because it's a simple technique, but really powerful for this kind of classification. KNN is normally used for classification and regression problems, and it works like calculating the similarities of the whole data set, and for this similarity we will calculate some distance, and after that we will make a prediction based on all the samples inside the data set and so on. And the algorithm has some steps that we have to calculate the distance in the whole data set, and we get the nearest neighbors. That's the name of the technique. So we can make predictions like considering the inputs of the user. Let's see this graph here. We can have this red point here, considering a new user input. So considering how we can configure the technique, it will give some answers, like the prediction for this example here. It is closer to the yellow one, so it will consider how the classes it will be predicted by the model. But if we configure like this k like 6 or kn, it will give different results. So that is more like what the learning technique will be doing behind the scenes when we have some.
So in here with this radius, it will be classified as purple, right? Because most elements we have here is purple.
Yeah.
But if you increase the radius to 6 neighbors, then we have more yellow samples, and the classification would change from purple to yellow, right?
Yeah. And with that, we can make some benchmark studies in the dataset. So what K will be better for this problem? It will be like testing all the Ks. We normally test like 3, 5, 6, and so on, depending. In the end, the accuracy or the statistics of the model will be based on what K you configure. But it's more like the KNN, how KNN works. Mm-hmm. And well, considering how we can how can we use the Cartesi API to create some the DApp structure? As you said, we can use the custom DApps for create the whole structure, but we can also include our Python files here and any other file that will be used for the DApp normally, as we can.
So just stressing here. So if you take a look at this file structure that he's showing from his application, and if you're curious, you can just check this repo here. It's the KNN1 inside the rollups examples on Cartesi's GitHub.
Yeah.
So you can see that in here you have a very familiar file when you're developing Python, which is a requirements.txt. So if you put a library in here, the framework will just have it available inside the Cartesi machine for your usage.
Yeah. And this file is also interesting because it will give the entry points of the DApp. Most of those files are pre-configured, so by the custom DApps. So you can read all the guides in the GitHub, and will be totally fine as a Web2 developer, or it will be easy to configure your DApp and make it work properly. Here we can see that we add the KNN.py, That I will be explaining
in details, right?
Yeah. As I'm explaining you, we have to have some distance for calculate the similarities of the samples. It's the first step of the algorithm. So in this example, I choose the Euclidean distance, but it could be any distance that could be calculated by 2 points, and the expression, the function, it's a Python function that you can easily calculate, getting the whole expression about the Euclidean distance, and it will get the 2 points that will be the samples of the, when we want to compare the similarities of the two samples, it will receive these two samples for calculate the distance. It will be done by every row in the dataset.
So this is basically the method that you use to evaluate from that picture of yours how far or how close from your point the other guys are, right?
Sure.
Cool.
It is like a 2D plan, so the points will be calculated with this function. Is the Euclidean distance, and then we will get in the really in the algorithm get the nearest neighbors, and it will get all the dataset we will have loaded in our variable here, and also the number of neighbors we'll be considering in the algorithm. So it will like call the Euclidean distance for every sample of the dataset, sorry, and it will have some variable here with all the distance of the depth. So it will.
So you go through all the points, you calculate the distances, and then you store the distances in this variable here.
Yeah. So we have this stored in this variable here, and we have some. We will use it for prediction too. When a new sample enters, it will be use the variables of this distance to get how close it is from one point to another. And we also have a neighbors list that it will be specified by the number of the entries, and then we will appending those neighbors based on the distance. So that is more like how the algorithm, the nearest neighbors works. It is when we are learning machine learning, that is the main algorithm that is all the academy teaches for us. So it's not like there is anything different for at all if I want to use this in any Web2 application. That is exactly how it is.
Exactly the same stuff you would do if you're not doing it on the blockchain, right?
Yeah, exactly.
Same code.
Same code, the same process, the same everything about this algorithm. No, I don't need to do any changes because I'm doing it in the blockchain. Not at all. It's just the same thing in Python, and that's it. And when we have a new input, we can make the predictions using the KNN classified function in this file, and it will give for you the prediction based on the whole dataset, the number of neighbors you configured it, and the prediction you consider like we explained it in the graph. Like we have a new prediction, and it will calculate how close it will be from the others, and it's all about the KNN, you know. And the implementation of it, again, it's not different from anything we will find in the internet. It's like we can search freely about, oh, I want a KNN algorithm. it will be something like that, especially with a search in Python or something.
So it's regular code written in Python that any AI researcher would use, right?
Yeah. Any AI researcher will be first doing its own, but it normally we can get the code and make some adjustment, like configuring. It's more important for an AI researcher to configure it properly to solve the problem. It's not like, okay, I know what I'm doing with the algorithm, but yeah, and I know what it is doing, but it's more a AI researcher job to configure it properly to work for the problem, you know. And that's it for the KNN code. When we are talking about Python specifically, and we will enter here in the how we can interact with the DApp. So it's the same command that you presented before. I'm just changing the
payload,
the
right?
payload. As I'm saying, the inputs are the size, the measurements of the iris you are doing, like the sepal length, the sepal width.
So sepal length, sepal width, then
petal length,
and
petal width.
Yeah.
The measurements are these four, and we use it for the
classification.
For
right?
the classification, you have some new example. You don't have the label of it. Okay, let's see what species is this flower. So this is the payload we are interacting with the DApp. And then we have the handle advance that it's coded to receive this kind of input and get the values and input in the variables for the the prediction. We have some auxiliary functions like hex to string, like that converts that are the auxiliary functions, but.
So just a parenthesis here. So the Cartesi rollups framework, it doesn't care about what you're sending. So this input from the Cartesi point of view is just something that makes sense to your application. And the way it's encoded is X encoded. So 0 to 9, A to F. And as Marcus said, in his case, his payload is actually a string. So this auxiliary method is converting from hex to the string format he's expecting as an input.
Yeah. And then when we send this, it will be like getting all the values of the JSON, in this case, of course, and then getting in all the variables for our prediction, you know. And then when we get all those variables, I will predict using the KNN classify, passing all the dataset, the values I'm just sent for the DApp, and also configuring the number of neighbors. And with that, we have some prediction, and we'll add this into a payload, saying that, okay, I received this, I processed it, and I predicted. I'm sending this back to using the requests, like the request posts, and we'll just send this notice to the Cartesi machine with the payload saying what I'm processing here, and in this case will be the class of the input. And then I think that is it for the handle advance at all.
So just as a recap, here you're processing the data you got using the KNN classifier.
Yeah.
Then once you have a prediction, you just retrieve it, encode it to be sent on a notice.
Yeah.
And that's it.
And that's it.
Awesome.
That is all we need for using this DApp, using the Cartesi API. And of course, we are seeing here where this file is, and we have in the GitHub all the guides for using it. in
And in case you're getting an error here, you're
Yeah.
catching an exception just like you do in a regular program.
Exactly.
And as I said before, in case of an error, you're not going to accept that input. You're going to reject it. Then you're going to throw a report to say what went wrong. And in these lines of code, he's just formatting the error message so that you can know what went wrong, right?
Exactly. Exactly. It's how you said before, like you will be setting the status to reject it, and that's it. If there is some problem with the prediction or something, that is the main road that the code will go. And it's, it's normal Python. Again, there is no worries about using Solidity, or it is Python. And then this is our front end. It is currently using all this backend that we explained. And then we have here the inputs that I just explained for you guys. We have all the petals and sepals measurements.
Dimensions, right?
Yeah. And we will also have the MetaMask with with the Goerli testnet. And then when we send the result, the transaction for the DApp, it will give you the answer saying what kind of flower is. And
so differently from before, we're actually using a web front-end in here, right?
yeah.
So you connect your wallet like you're used to on any Web3 application. In this case, it's connecting to the Goerli Ethereum testnet. And once you input this stuff, you're going to create a transaction. It's going through the blockchain.
Yeah.
The Cartesi framework takes care of it, so it hits that handle advanced method.
Yeah.
And then when you get response using the notices, you display the correct flower.
Exactly. Exactly. And speaking more about this front end, the whole development of this was like normal Web 2 development, considering the interfaces like the GraphQL, the HTTP, and the inspect that we don't use it in this case, but again, all the other things was normal Web 2 development, nothing else. And with all this was only possible because we are using the Cartesi API. Here is another example, like saying we have different measurements, and then we have a different class.
So in the previous one, which was the flower?
Was
Iris setosa.
Iris setosa, and this one is Iris versicolor. So we gave them different measurements, different results. It shows that we are really processing stuff with machine learning in the Cartesi machine. That's it.
Okay, I guess that's it, boys. If you have any doubts or anything, we're always available on Discord. Our community is really friendly. So it doesn't matter if you don't know how to program, we can help you get started. Or if you're a kernel hacker that is into fine-tuning the scheduler parameters, we're free for all. Okay? Yes, that's it, mate. Have a good night.